Go into the bathroom.
Take your seat, please. Now let's see. Let's see what we came up with. So what we want to do is kind of come up with a generic rule of thumb. If I'm talking about my height to my wingspan, what's the common ratio that we accept that as? 1 to 1. Yeah. Yeah. So if you ever look at Michael Jordan do this, in fact, there's that one famous picture of him palming the basketball where he's got his arms like that. You're like, man, look at his arms. That's because he's that tall, right? That's supposed to be a 1-to-1 story. You know why? One of the reasons why Michael Phelps is such an amazing swimmer, his arms are longer. He's out of proportion. So what makes him excel physically, other than all of his hard work, determination, grit, dedication, practice, you know, all that kind of stuff. Just physically, he was set up for success because his arm span is so much longer, and that helps him swim faster. Okay? What about your arm span to your waist? What'd you figure out there? That's about half, yeah. So we used to tease that if you're not in the mood to try on pants or whatever you're shopping for, you know, you can see if the pants are halfway across your arms because your arm span is double your waist. Okay, how about one time around your waist to one time around your neck? What you come up with there? That's supposed to be a 1-to-2 ratio. So if you wanted to check your waist, see if you can wrap it twice around your neck, they should be the same, right? So let's talk about these because we can take these ratios and make some jumps into these connections. If arm span to height is 1 and arm span to waist and waist to neck, right? So we have that conversation about arm span is 2 to 1. I guess I wrote this backwards. This is also going to be 2 to 1 if I'm talking about waist to neck. So how do I compare arm span to neck? What should that story be? Think about it. Arm span to waist is 1 to 2, right? Okay, 4 to 1 or 1 to 4? If I'm going arm span to neck, 4 to 1. So we're going to stay with 4 to 1. And remember, we talked about the difference between a scale factor and a scalar. If I had my neck and I wanted to know how tall I was, I would multiply it by 4. So make sure you're keeping track of that scale factor versus the scalar. All right, distance around my head to the length from my shoulder to my wrist. What was that? Yeah, it's supposed to be 1 to 1. Yeah. So theoretically, Michael Phelps should have a fat head, right? Right? Theoretically. So if we have that distance around our head and our distance around, or from our shoulder to our wrist, should be a 1 to 1 story. My favorite is when we're not masked and I ask the kids about their pinky and their nose. And one of the most entertaining views as a teacher is this one. When you all at the same time do this. It's supposed to be 1 to 1. Are you in proportion? I have a really long nose. So I guess that's why I have a really long pinky. I don't know. I'll keep my nose covered up. So your pinky to your nose is supposed to be 1 to 1. How about the base of your thumb? The length of the circumference of the base of your thumb to the circumference of your wrist. What you come up with there? Wrist and thumb? So Maggie's putting 1 to 3 out there. Anybody else? Take your measurements, and you might need a friend to help you with the measurements, or at least to read them. Grab a calculator if you need it, for crying out loud. but measure it. Maggie got 1 to 3. Are you 1 to 3 or 1 to 2? Are you 1 to 2? Did I hear Ethan? Was that you?
1 to 2.
1 to 2. Maggie says 1 to 3. Maybe she's got skinny thumbs. Or big wrists. Muscular,
the
right?
difference between
Right?
the 1 to 2, like my number is exactly in between 1 to 2
Yeah.
and 1 to 3. So.
So 1 to 2.5. Something like that.
1
Okay.
to 3.
And then we can talk about how to do with your wrist, the length of the circumference of your wrist to your neck. What was your wrist to your neck? Did you get that far? 1 to 2? Doesn't it seem like it would be more than that? Right? Wrist. So then you can go from your wrist to your neck to your waist to your height. How about that? All those proportions that exist inside our body. Kind of cool. All right. So what I would like you to do right now is let's have whoever is in quadrant 1 collect the take measures, return them to the basket. Whoever's in quadrant 2, come see me for notes for your classmate.
I'm always in quadrant 1, no matter where I go.
Wait, how do you know which word?
For me, 3.
Did I give you 4?
The James is absent.
Okay, just put them back. Thank you. Put one back.
Just 2. Okay,
4.
Too many? Thanks, Emery. Thank you. Too many. So, please don't file that or put it away. We're going to come back and talk about a couple of the problems that were in your homework that I collected last class. So I passed it out. Please have it out and handy and ready because in about 5 minutes I'm going to ask you to pull it out because we're going to talk about and I'm going to see if you were savvy enough to figure out a shortcut or not. All right, here we go. Note 6.3. Again, we're not creative when we name things in mathematics. So here we've encountered our side splitter theorem. So ratios and proportions are just the funnest thing to teach in mathematics because it truly is all about the relationships between things. Geometry, we love shapes. So of course we're naturally curious about the relationship between all of those shapes. Where do you see the right triangle ones that we're going to talk about at the beginning of next unit? They're so very cool. So as mathematicians, we're studying similar triangles. And in fact, being able to use, this is called indirect measurement, being able to use similar triangles, similar figures, to use those ratios and proportions to measure things was mind-boggling because suddenly mathematicians could measure things that were bigger than they were ever able to, like distances across rivers or distances like the heights of the pyramids or whatever they needed to measure. They could do indirect measurement by creating similar triangles and being able to look at their proportional relationships. One of the relationships that they came up with is called the side splitter theorem. And again, we're not creative when we name things in mathematics. But what they basically said is if a line is parallel to one side of the triangle and intersects the other two sides, then it divides the sides proportionally. So let's pick this apart and see what it says. If a line parallel to one side of the triangle, so we're talking about this guy here. So line segment TU is parallel to one side of the triangle and it intersects the other two sides. So here's our one side it's talking about and it intersects these two sides. Because of our proportional relationships, I know that this line segment TU is going to divide QR and SR proportionally. So QT and SU form a relationship. Think about where it is, QT and SU. And if it's easier for you to go ahead and call this A and B and C and D, you can go ahead and do that. Because I know that the relationship between A and B is going to match the relationship between C and D. Now notice, whenever I do this, I give it to you two ways, because here's the hardest part about proportions, is people don't always write them the same way. They see them differently, but that doesn't mean they're wrong. So if I ever present you with a proportion and you're tempted to go, I don't know if mine's right, I wrote it differently, I'm not sure, what's our test? How do we test to see if our proportions are the same? Yeah, the cross products. Because if you look here, I wrote QT on top and TR on the bottom. Here's SB on top and UR on the bottom. Do you notice that my cross products are always the same? So whether I compare these two cutoff pieces to these two cutoff pieces, or the two pieces of the same line to the two pieces of the same line, they're both going to be a true story. Now it's interesting, I find kids either see one first or the other first. Check in with your partner. Do you see the piece to piece or the part to part? Ask your partner which one they see. Go. I always love it when I have a kid that's like, I don't see anything, I don't get it. Anybody with me there? I don't see anything, I don't get it. When we look at proportions, one of the hardest things that we do is jump into someone else's brain, right? So whether you're talking about a relationship within one triangle compared to the other triangle, or relationships across the triangle, it's important to pay attention to what naturally makes sense to us. This warning is an interesting one, and we're going to come back to it. And what I want you to star and circle it, because you know how I keep telling you, don't be that kid that makes this mistake? Remember how I say, like, don't be that kid that makes this mistake? Here is this warning. This parallel line only splits the sides. If you're messing around with finding the measurements of this base, that base is not a part of the side splitter conversation, and you're going to have to use the measurements of the whole triangles. And I'm going to put a pin in that. We're going to get back to that in 2 seconds. Now, of course, when we talk about something and its converse, we can talk about if, then, and then our converse asks us to what, to do what to the hypothesis and the conclusion. Yeah, flip it around. So we say, if a line is parallel, then it's going to divide it proportionally. What's my converse going to say? If it divides it proportionally, then, yeah, so now we have another way of proving parallel lines. You're like, that's just what I needed. I woke up this morning and I was like, gosh, I wish we had another way of proving parallel lines. There you go. So if a line divides two sides of a triangle proportionally, then it's parallel to the other side. And then we have these conversations about giving these values. If this is true, then the lines are parallel. Okay. So we're going to come down here. We're going to talk about a corollary to our side splitter theorem. And while we're here, we might as well mention this nugget. That's basically what a corollary is. So anytime you're like, oh, I got something that's kind of sort of related to it, but a little bit separate, deserves its own time, but I want to talk about it at the same time, that's a corollary. So while we're talking about this side splitter theorem, while we're here, we might as well talk about if I have 3 parallel lines. I could talk about having 4 parallel lines. I could talk about having as many parallel lines as I want, because if 3 lines intersect 2 transversals, then they divide the transversals proportionally. If 4 lines intersected 2 transversals, they would divide those transversals proportionally. So do me a favor, really check in and read this, and I want you to mark up what you see is parallel or not parallel. Mark up your drawings, and I want you to note which lines are parallel, and I want you to note which lines are divided proportionally. Give it some A's and B's. I'll give you your baskets back. I forgot to after our cell day. Use a highlighter, a pen of another color. Really mark up so that what you're talking about in your notes, because we want to make sure you're looking at the right thing. Olivia, we're doing what you always do. Put some color on it. So here's what we're talking about. Ready? If these are my parallel lines, and they're intersecting my transversals are going to be divided up evenly. So let's talk about my transversals. Here's my transversal L, and I'll note him in pink. And here's my transversal M, and I'll note him in green. So it's saying that if all of these lines are parallel, they chop up these transversals into different pieces. So the distance from U to W, I'll write as A. The distance from V to X, I'll write as B. WY, I'll call C. And XZ, I'll call D. So just like we said above, each of these transversals is divided proportionally. So basically, if I knew 3 out of 4 of these values, I could solve for the one that I'm missing. And again, however you write your proportion, whether you're comparing A to B, piece to piece, or whether you're comparing A to C, part of this line to part of this line, A to B and A to C are going to have the same relationships as C to D or D to B. So depending on how you see that proportion, do you see these 2 pieces compared to these 2 pieces? Because that's a true story here. Or do you see these 2 pieces compared to these 2 pieces? That's the story here. Go ahead.
So when you talk about proportions, you mean that like A to C would have a 1 to 2 ratio, and then B to D would have the same ratio?
Yeah. So whatever the ratio is, whatever happens up here happens down here. Okay? All right. So we're going to come back to the angle bisector theorem in a minute, but what I want you to do is you flip your paper over, and I want you to look back at, and I want you to look at your homework that you did. So take out that 6-2, because these are the same problems. These were side splitter problems.
The one that we got back.
The one that I handed you back just now. Where it asks you to solve for x, there's 4 triangles. 4 sets of triangles. 8 triangles to be exact. 2 of the triangles can be solved using the side splitter shortcut, and 2 cannot. With your group, would you please decide which 2 fit the side splitter and which 2 do not? Everybody with me? Yeah? Okay, and your mark is set 12.
Top right and top right.
To figure it out?
Yeah,
Yeah, how come?
because the things are on the sides, so we can set up an equation here.
You see it? Because these ones have all the base. So you can't use the side, no, they are solvable. So you solve for
The
them
ones that involve the base.
here, right?
Side splitter,
These will be sides.
this, and this.
Oh, but it's not.
Yeah.
Yeah, do you see it?
Yes, the base is.
Oh, okay.
The bottom right you can't do.
All right, so I'm gonna go ahead and call this one A. I'm gonna call this one B. I'm gonna call this one C. And I'm gonna call this one D. Which two can I not use the side splitter for?
B and D.
Rachel says B and D. Thumbs up if you agree. Yeah, me too. So what's interesting is we made you write the following proportion for this. We said that x is to x plus 5 as 12 is to 19. Don't write that down because that's what you should have written down in your homework to solve. So the really cool thing about this is when we talked about this small triangle and we were comparing it to this big triangle, we had to say that this side was x plus 5. So x to x plus 5 is the same as 12 to 12 plus 7, and that's where that 19 came from. That's how we asked you to solve it before. And you did. Many of you. Now what we're saying is go ahead and do x to 5 is the same as 12 to 7. Notice it's simpler. I don't have to distribute, and I'm working with smaller numbers. Aren't we always happy to work with smaller numbers? 7x is equal to 60, x is equal to 60 over 7. When you got 60 over 7, is that the same answer that you got before? Should have been. Because our side splitter theorem allows us to take this shortcut. So if you forget the side splitter theorem, that's okay. You can still go about solving it the old way. But you know in geometry, we're all about finding a better, smarter, faster, more efficient way of doing things. So this is the one theorem, this is the one shortcut that mathematicians came up with. So Rachel says you can't use this with B, and I agree with her. Who can tell me why? I'm so excited about this, I want to do it here. And I want to write x is to 20 and 11 is to 9. Rachel's over here going, told you no. Olivia's going to tell me why.
It's because when you're using the theorem, you can't use base angle for.
When I'm using the side splitter theorem, I can't use base. It's the side splitter theorem. Everybody say it. It's the side splitter theorem. Do you hear the word base in that? No. So there's no bases allowed. So when I'm talking about what's divided proportionally, if I wanted to talk about these two values, heck yeah, they would be fine. But that's not what the story is that I'm telling. So if I'm given a base part of the conversation, I need to go back to that idea of two similar triangles, that they share this angle. And I know I have a 9 and 11 story, and I know I have a 20, and what's the length of this side? Yeah. So I can't take the shortcut with this one. I have to set it up the same way that I did in my homework. I have to go ahead and say that, and you can do 9 is to 11 as 20 is to x plus 11. Now, if you're sitting there saying, I didn't set mine up that way, If you did 9 to 20 is equal to x plus 11, you just flip-flopped your means. You're okay. As long as when you're solving this, you're multiplying 9 times x plus 11, and you're multiplying 20 times 11, as long as those are your cross products, you're fine. Check in with your partner and see if they set up the proportion the same way you did. Check in with them, ask them, go.
For which? No, I didn't. I think I did that wrong. So I didn't know. Oh, okay.
Okay, who's gonna fess up that they did it wrong on the homework? Yeah, go put a smarty up, Abdullah. I'm proud of you for fessing up. Yeah, because a lot of you, when you solved it on the homework, you were doing the side splitter. But first of all, you hadn't learned it yet. Second of all, you can't do it. So you got away with it for problems A and C, but not for B and D. So thank you, Abdullah, for being honest. Now that you know I'm giving smarties out, anybody else want to fess up that they did it wrong in the homework? Go to them. Yeah. So here's the thing, we need to make sure that we're understanding when I can take a shortcut and when I can't. So if you're gonna be taking shortcuts illegally, you're gonna get caught, right? So we wanna make sure that you're doing it right. All right, put 6-2 away, put your old homework away, don't peek at it, and do C and D on your own now. Get a calculator if you need to. Don't peek at the homework, and do C and D, and you're about to set go. Oh yeah, quadrant 3. Go get calculators for your table groups.
Yeah.
Quadrant 4 is next.
Oh, really? Wait.
I want to talk to you about answer D. I got 110 divided by 8. So that's a terminating decimal. If you told me 13.75, I'd be okay with buying that. But a lot of times we prefer our answers to be left as fractions, because chances are we're still working with the number. And it's easiest to leave it in fraction form. Does anybody know how to put this back into a fraction? Math. Yep. Say it out loud, everybody. Math. Math. This is not a simplified value. This is. This is the best answer. This is the one that makes me smile on the inside. I'm like, oh, they were listening. Those are the ones I like. All right, so we didn't quite finish the notes. So I'll ask you to flip over and go back and talk about the triangle, angle, bisector theorem. Now later on, I'm going to show you the proof of this. And the proof of it is kind of cool. I'm not going to make you do it. But it totally has to do with the side splitter theorem, which is why it's in this why it's in this section. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So this is one of those theorems that I gotta tell you something, kids always forget it, and they'll be staring at a problem, and they'll be like, I don't get this one, because they're looking for similar triangles, or they're looking for parallel lines, and they're not gonna find them in this problem. And I will say to that kid who's struggling with that problem, this is the one. And they'll be like, oh, because I'm telling you right now, when you've exhausted every opportunity about how to defend the relationships between the sides, kids spend all kind of time. They're like, is it median? No, it's not. Is it angle bisector? Yes, it is. Does it create the in-center? No, because I don't have other angle bisectors. And you're struggling to realize what the proportions are. This triangle angle bisector theorem is the one everybody forgets. Do yourself a favor and call this A. Call this B. Call this C. Call this side D. If CD is an angle bisector, which my friends it is, then I know that I can say that the side of the triangle that's split is going to be proportional to the two sides of that angle that's been bisected. So A to B is going to be the same as C to D. And you can justify that by using either proportion. You can either compare A to B, this piece to this angle side, this piece to this angle side, or you can talk about these two sides compared to these two. Whichever way you want. Because basically what this last unit about, or what this last section is about, is just giving you more relationships that can help you solve for unknown values by solving proportions. Sound okay? All right. So on the back of this piece of paper, you have 2, 3, and 4. This graphic here is the one that explains and justifies that triangle angle bisector theorem. So I want you and your group mates working on problems 2, 3, and 4. And then we'll talk more about 4 when you end up coming back from lunch. So I want you working up until the bell rings, ask questions we don't understand, talk to your group mates. Your mark is set, go. Work.